The water is clear, not blue the way we imagine oceans, not the deep dramatic blue of travel photographs or nature documentaries. Clear, the kind of clear where sunlight reaches the bottom 60 feet down and lands on individual coral heads with enough precision to cast shadows. The sea that sits above what will one day be called the Yucatan Peninsula is shallow and warm and extraordinarily alive. It has been this way for millions of years. It will not be this way much longer. A school of fish moves through the coral in the slow, unhurried rhythm that fish have maintained for 300 million years. They are not nervous. There is nothing to be nervous about. The morning is ordinary in every way that a morning 66 million years ago can be ordinary. The water temperature is comfortable. The currents are gentle. On the seafloor below, a mosasaur rests in the way that large predators rest when they are not hungry. Passionate, still, aware of everything and concerned about nothing. On the coastal plain to the north, beyond the shoreline, the land is dense with vegetation. Not the forests we know. No oaks, no maples, no flowering trees of any kind that would look familiar, but dense, green, layered from the ground to the canopy in the way that only 66 million years of uninterrupted evolution can produce. The air is warmer than today. The oxygen content is slightly higher. Everything that lives here has been shaped by conditions that have been stable, more or less, for longer than the human mind can honestly process. This is the world on the morning of a day that has no name. The animals moving through it have no awareness that anything is different. The hadrosaurs feeding at the forest edge cannot look up and see what is coming. The pterosaurs riding the warm coastal thermals cannot detect it. The mosasaur on the seafloor cannot feel it. What is coming has been traveling for millions of years through empty space, completely silent, and it is now close enough that the distance remaining can be measured in seconds. None of what you are looking at will survive the morning. If you find yourself wanting to understand how a world ends and what it looks like from inside the last ordinary moment before it does, please subscribe to this channel. This kind of work takes time to research and to build. Your support is what makes it possible. Thank you. Part the world at 6:00 a.m. To understand what was about to be destroyed, you have to understand what it actually was. Not in the abstract way that documentaries usually handle this. Not a list of species names and geological periods and Latin classifications. What it actually was. The texture of it. The weight of it. The 66 million years of accumulated biological complexity that was, on this particular morning, simply going about its business. The Cretaceous world, at the moment of impact, was not a primitive world. That is the first thing to correct. We have a tendency to think of ancient ecosystems as simpler versions of what we have now. Rougher drafts, earlier attempts. They were not. The late Cretaceous was a fully realized biological system of staggering complexity. The product of 4 billion years of unbroken evolutionary experimentation. And in many respects, it was richer and more diverse than the world we inhabit today. Start with the geography, because the geography determines everything else. The planet, 66 million years ago, would not be recognizable on any map you have ever seen. The Atlantic Ocean exists, but it is narrower. North America is divided into 2 separate landmasses by a vast, shallow inland sea called the Western Interior Seaway, running from what is now the Arctic Ocean all the way down to the Gulf of Mexico, splitting the continent cleanly down the middle. Everything west of this seaway is one landmass. Everything east is another. They are not connected. If you were standing in what is now Denver, Colorado, you would be looking out at open ocean to the east. This inland sea is not incidental to the story. It is the reason the region around Chicxulub is what it is. The shallow, warm waters of the seaway and the adjacent gulf have been producing limestone for tens of millions of years. Layer upon layer of compressed marine organisms settling to the seafloor and solidifying into rock. The crust in this region is thick with calcium carbonate and sulfur-bearing minerals. This specific geology will matter enormously in approximately 2 hours. But we are not there yet. The temperature on this morning is roughly 10 degrees Celsius warmer than the global average today. Not uniformly. The poles are warmer relative to the equator than they are now, meaning the temperature gradient from equator to pole is gentler. There are no permanent ice caps. The sea level is higher. Large portions of the continental interiors that are dry land today were shallow seafloor 66 million years ago. In this world, the dominant large animals on land are the non-avian dinosaurs, and they have been dominant for 165 million years. That number is worth sitting with for a moment. 165 million years. For comparison, the entire evolutionary history of our own genus, Homo, spans roughly 3 million years. The dinosaurs had been the uncontested rulers of terrestrial ecosystems for more than 50 times that long. They were not a temporary arrangement. They were not an experiment in progress. They were the established order of life on land, refined and perfected over a span of time that makes our own history look like a rounding error. On the coastal plains of what will become Texas and New Mexico, herds of hadrosaurs are moving through the early morning. Hadrosaurs are the most abundant large herbivores in North America at this moment. They are not the lumbering, slow-witted creatures of older reconstructions. They are social animals, moving in coordinated groups, communicating through a repertoire of sounds produced by the elaborate bony crests on their skulls. Some species have crests that function as resonating chambers, producing low resonant calls that carry for long distances through the forest. They are warm or near warm-blooded. They move with purpose. They are, by any reasonable measure, successful to the west. In the forests and floodplains of what will become Montana and Wyoming, Tyrannosaurus rex is already old news. The largest tyrannosaurs are not the apex predators they once were in the public imagination of scientists from an earlier era. They are ambush hunters, slower than the hadrosaurs they prey upon, relying on power rather than speed, capable of delivering a bite force that no land animal before or since has matched. A full-grown Tyrannosaurus weighs somewhere between 8 and 14,000 kilograms. It does not chase its prey across open ground. It waits. It approaches. It ends things quickly. In the skies above the coastal plains, pterosaurs still fly. Quetzalcoatlus, with a wingspan of up to 10 meters, is the largest flying animal that has ever existed or ever will exist. It does not flap continuously the way smaller birds do. It soars on thermals, covering enormous distances with minimal energy expenditure, scanning the ground below with eyes that are proportionally larger than those of any modern bird of prey. It lands awkwardly, folds its wings, and walks on all 4 limbs with surprising efficiency. It is strange, and it is magnificent, and there is nothing else like it anywhere in the world. In the shallow seas that cover much of the continental interior, mosasaurs are the dominant predators. They are not dinosaurs. They are large marine lizards, distant relatives of modern monitor lizards, that evolved into fully aquatic hunters over tens of millions of years. The largest mosasaurs reach 14 meters in length. They are fast, agile, and equipped with 2 sets of teeth, one on the jawbones and one on the roof of the mouth, allowing them to grip struggling prey and work it toward the throat with a ratcheting motion. The Western Interior Seaway is their ocean. They have no serious competition. Beneath all of this, small and largely invisible, are the mammals. They have been here since the Triassic, almost as long as the dinosaurs themselves. But they have never been able to expand beyond a narrow range of ecological roles. They are small. Most of them are nocturnal. They live in burrows, in rock crevices, under leaf litter. They eat insects, seeds, small invertebrates. The largest mammals alive on this morning are roughly the size of a modern badger. They are not dominant. They are not even particularly visible. They are simply there, occupying the margins of a world that belongs, completely and without serious challenge, to something else. This is the world at 6 in the morning. It has been this version of itself, more or less, for millions of years. The species have changed. The specific genera have turned over. But the basic structure, large dinosaurs on land, mosasaurs in the sea, pterosaurs in the air, small mammals in the margins, has been stable for longer than most geological periods last. It is about to change in a single morning. The object that will change it is not yet visible from the surface of the Earth. It is approaching from a direction that puts it on a shallow angle of entry, which will matter. It is moving at roughly 20 kilometers per second, which will matter more. It is approximately 12 kilometers in diameter, roughly the distance from one side of a large city to the other, and it is composed of rock and metal in roughly equal proportion. At 20 kilometers per second, the surface of the Earth is less than 90 seconds away. Par deux. The moment of impact, the physics of the end. There is a moment, in the last second before impact, when the asteroid is still technically in the atmosphere, but the atmosphere no longer matters. The air in front of it cannot get out of the way fast enough. At 20 kilometers per second, the rock is moving faster than the air molecules can transmit the information that something is coming. What builds up in front of the asteroid is not a cushion of compressed air. It is a wall of superheated plasma. Temperatures reaching tens of thousands of degrees Celsius, hot enough to vaporize steel in milliseconds. The asteroid does not slow down meaningfully. The atmosphere, for an object this size, moving at this speed, is not a barrier. It is barely an inconvenience. The asteroid hits the shallow seafloor of what is now the Yucatan Peninsula at an angle of approximately 45 to 60 degrees. This angle is not random, and it is not trivial. A steeper impact would have driven more energy straight down into the crust. A shallower one would have skipped more energy into the atmosphere to the north and east. 45 to 60 degrees is, by a brutal coincidence of orbital mechanics, close to the worst possible angle for the creatures living on the planet it is hitting. It maximizes the volume of vaporized sulfur-bearing rock ejected into the upper atmosphere. It directs the most lethal debris field toward the most densely populated continental landmass in the Western Hemisphere. If the asteroid had arrived at a different angle, the story of the next 66 million years might have been different. It did not. At the moment of contact, the word explosion becomes inadequate. An explosion is a rapid release of energy from a contained source. What happens at Chicxulub is not contained in any meaningful sense. The energy released in the first second of impact is equivalent to roughly 1 billion times the energy released by the atomic bomb dropped on Hiroshima in 1945. That comparison is standard in discussions of this event, and it has become so familiar that it has lost most of its power to communicate anything real. So consider it differently. The total energy released by every nuclear weapon ever built or tested by every nation in the history of human civilization, if detonated simultaneously in a single location, would represent approximately 1% of the energy released at Chicxulub in the first few seconds of impact. Every weapon, all at once. 1%. In the first fraction of a second. The asteroid and the top several kilometers of the Earth's crust in the impact zone are not broken or displaced or melted. They are converted directly from solid rock into plasma. Not heated. Not melted. Converted. The distinction matters because it means the energy is released almost instantaneously into a volume of material that can no longer absorb or distribute it in any conventional physical sense. The plasma expands outward at velocities that exceed the speed of sound in rock by factors of 10 or more. The crater that begins forming in the first second is not dug. It is blown. The surrounding rock does not fracture and fall inward the way the sides of a pit collapse when you dig a hole in sand. The rock flows. Under the pressures generated in the first moments of impact, solid granite behaves like a liquid. It moves in waves. It splashes. A ring of mountains higher than the Himalayas forms around the impact site within the first 2 minutes, then collapses back inward under its own weight within the next 10, leaving a circular scar roughly 180 kilometers across at 2 seconds after impact. The ground moves, not shakes, moves. The seismic wave propagating outward from Chicxulub through the body of the Earth is not comparable to any earthquake in recorded human history. The largest earthquake ever measured by modern instruments, the 1960 Valdivia earthquake in Chile, registered magnitude 9.5. The seismic energy released at Chicxulub in the first moments of impact is estimated to be equivalent to a magnitude 10 or 11 event. The difference between magnitude 9.5 and magnitude 11 is not a difference of degree. It is a difference of kind. Each full unit of magnitude on the Richter scale represents roughly 32 times more energy. Magnitude 11 is not slightly worse than magnitude 9.5. It is thousands of times more energetic. This wave moves through the rock at several kilometers per second. It will reach the opposite side of the planet in roughly 20 minutes. Along the way, it will trigger every fault line it passes through. It will cause volcanic systems that were previously stable to become unstable. It will do this silently and invisibly, deep in the crust. Long before any surface effect of the impact is visible from a distance, at 30 seconds after impact, the ejector begins to leave the atmosphere. Ejector is the material thrown outward and upward by the force of the impact. Some of it goes sideways, devastating the immediate region, but a significant portion of the material, superheated rock and steam and in vaporized crust, is moving fast enough and at steep enough angles that it exits the Earth's atmosphere entirely. It goes into space. Pieces of the Yucatan Peninsula, melted into glass beads and droplets of resolidified rock called spherules, travel briefly through the vacuum above the atmosphere before gravity begins to pull them back down. They will re-enter the atmosphere over the next hour, distributed across the entire surface of the planet, each one generating heat through friction as it descends. This is the mechanism that will matter most in the next hour. Not the crater, not the local devastation. The spherules, at 2 minutes after impact, the fireball is visible from a distance of 2,000 kilometers, not as a distant light, as a replacement for the sky, from the Gulf Coast of what will become North America, from the shallow seas of what will become the Caribbean. The entire southern horizon is not bright. It is white. The distinction between the fireball and the sky around it does not exist at this distance. There is simply a direction in which looking is no longer possible. The sound has not arrived yet. Sound travels through air at roughly 1.2 kilometers per minute. The fireball is visible at 2,000 kilometers because light travels essentially instantaneously at these distances. The sound of the impact, the actual acoustic wave, will not reach 2,000 kilometers away for roughly 27 hours. The animals on the Gulf Coast that are already responding to the light in the sky, already moving, already behaving in ways driven by instinct towards something they have no framework to understand, will not hear the impact that is killing them for more than a day after it happens. They will be dead long before the sound arrives. At 5 minutes after impact, the crater has reached its maximum temporary diameter of roughly 200 kilometers and has begun to collapse inward. The central peak, a mountain of rebounding crust pushed upward by the elastic rebound of the compressed rock below, rises and falls within minutes. The final crater that will be preserved in the geological record and discovered by geologists in 1991 is not the maximum size reached by the impact structure. It is the settled, collapsed, partially filled remnant of something that was briefly much larger and much stranger. At 10 minutes after impact, the first spherules are beginning to re-enter the atmosphere over North America. The first 24 hours have barely begun. Pas 3. The first hour, a 2.0 km radius, on the coastal plains of what is now Texas, roughly 1,800 kilometers from the impact site. The morning has been ordinary until this moment. A hadrosaur herd of perhaps 40 individuals is moving along a river channel, following the water, the way large herbivores have always followed water. They have no awareness of what happened 90 seconds ago to the south. The seismic wave from the impact is already moving through the rock beneath their feet. But the rock here is thick, and the wave has not yet reached the surface in a form they can detect. The air is still. The birds, the small feathered dinosaurs that will one day be the only surviving members of their entire lineage, are still calling from the tree line. Nothing has signaled that anything is wrong. Then the sky to the south changes color. Not gradually, not in the way that a storm approaches or a sunset develops. The southern horizon goes from the ordinary pale blue of an early morning sky to something that has no color category in the experience of any animal alive on this planet. It is white, in the way that the inside of a furnace is white. It is not a light that illuminates the landscape. It is a light that replaces the sky. The hadrosaurs stop moving. Every animal in the region that has eyes stops moving. The response is instinctive and universal and completely useless. They are looking at the thermal radiation front of an impact fireball traveling toward them at the speed of light. And there is nothing in 66 million years of dinosaur evolution that has prepared any of them for this information. The heat arrives before anything else, not the heat of fire. Fire requires fuel and oxygen and time. What arrives in the first minutes after the light changes is radiant heat, the same mechanism by which the sun warms the surface of the earth, but compressed into minutes, rather than distributed across a day. The rocks begin to warm. The surface of standing water begins to warm. Leaves on the sun-facing sides of trees begin to warm in ways that leaves do not warm under normal solar radiation. At this distance, 1,800 kilometers from the impact site, the radiant heat pulse in the first hour is not immediately lethal to large animals. It is deeply wrong in a way that biology has no protocol for. It is the kind of wrong that causes animals to move without knowing where to go. The hadrosaurs begin moving north, away from the light. Not because instinct tells them north is safer, but because instinct tells them to move away from the thing that is not right. And north is simply the direction that is not the thing that is not right. They will not outrun what is coming. Meanwhile, in the shallow waters of the Gulf, the ocean is doing something that oceans do not do. The impact has displaced an enormous volume of water, not in the way that a stone dropped in a pond displaces water, creating a neat circular wave. The displacement at Chicxulub is more fundamental than that. The seafloor in the impact zone has been removed. Not cracked, not depressed, removed. The water that was sitting above it has fallen inward toward the crater and then rebounded outward in a wave that is not comparable to any tsunami generated by an earthquake or a volcanic eruption in recorded human history. Tsunami is technically the correct word for what propagates outward from Chicxulub across the Gulf of Mexico in the first hour after impact. But the word carries associations with events that, while catastrophic by human standards, are physically of a completely different order. The tsunami generated by the 2004 Indian Ocean earthquake, one of the largest in recorded history, had open ocean wave heights of roughly 0.5 meter to 1 meter, reaching maximum heights of 30 meters only when it compressed against shallow coastal shelves. The wave propagating outward from Chicxulub in the first hour has open ocean heights estimated at several hundred meters. When it encounters the shallow continental shelves surrounding the Gulf, it does not simply grow taller in the way that normal tsunami waves grow taller. It behaves differently. The sheer volume of water involved means that the wave does not pass through a location the way a normal wave passes through. It arrives and it stays, pushing inland for distances of tens of kilometers before the water has anywhere to go. The coastlines surrounding the Gulf of Mexico in 66 million years before the present do not exist in the same configuration as modern coastlines. The western interior seaway opens to the north. The land is lower. The wave has more room and less resistance than it would find on modern coastlines. What moves inland across the coastal lowlands of North America in the first hour is not a wall of water in the dramatic sense that the phrase implies. It is a rapid and sustained rise of the sea across terrain that has never experienced anything like it, carrying with it the sediment and debris of the seafloor, depositing it tens of kilometers inland in layers that geologists will eventually find and correctly identify as evidence of the impact. At the same time, in the sky above North America, the spherules are arriving. Each individual spherule is small, a few millimeters in diameter, a tiny glass bead of resolidified rock that was briefly part of the Yucatan Peninsula before being thrown into space and pulled back down by gravity. Individually, they are almost nothing. Collectively, they are the most efficient delivery mechanism for thermal energy that the planet has ever experienced or will experience. As each spherule re-enters the atmosphere, it generates heat through friction. This is the same principle that makes meteors visible as shooting stars. A single meteor generates a streak of light and a brief pulse of heat that dissipates harmlessly into the upper atmosphere. 100 trillion spherules re-entering simultaneously do not dissipate harmlessly. They transfer their energy to the atmosphere as heat, and the atmosphere transfers that heat downward to the surface below. The effect at ground level is not fire falling from the sky. It is the sky itself becoming a source of heat. The mechanism is identical to what happens when you open an oven door. The heat does not come from a single point. It radiates from above, from an entire hemisphere of superheated atmosphere, downward onto every surface that is exposed to the sky. At this level of thermal flux, dry vegetation ignites without flame contact. The surface temperature of exposed rock rises sharply within minutes. Animals caught in open terrain with no access to water or underground shelter begin to experience thermal stress within the first 30 minutes of spherule re-entry, and lethal heat exposure within the first hour. The animals that survive the next hour will be the ones that are underground, underwater, or in terrain that provides natural shielding from above. Not because they are faster, not because they are smarter, because they are in the right place by chance. in burrows, in caves, in river channels, beneath overhanging rock, below the surface of water that is warming but has not yet reached lethal temperatures. The hadrosaur herd that was moving north along the river channel 1 hour ago no longer exists as a herd. The river channel still exists. The water in it is warmer than it was. The trees along its banks have begun to burn on their upper canopy. The exposed crowns, taking the radiant heat first, while the trunks and root systems, shielded by the canopy itself and the moisture in the soil, remain intact for now. The fish in the river are still alive. The small mammals in burrows beneath the riverbank are still alive. The insects in the soil are still alive. Everything that was visible from above an hour ago is either dead or dying. By the end of the first hour, within a radius of roughly 2,000 kilometers from Chicxulub, the surface of the world has been transformed in ways that have no precedent in the experience of any living thing. The seismic waves have passed through. The tsunami has moved inland and is beginning to recede, leaving a landscape of deposited sediment and destroyed coastal vegetation. The spherule bombardment is ongoing. The fires are beginning. The rest of the planet has not yet felt any of this directly. In Asia, in what will become China and India and the islands of Southeast Asia, it is the middle of the night. The sky is dark and clear and full of stars. The dinosaurs there are sleeping or moving in the quiet way that large animals move at night. The air is ordinary. The ground is still. The seismic wave from Chicxulub is moving through the deep rock toward them at several kilometers per second, and it will arrive within the next 20 minutes. But it has not arrived yet. They have no idea what the next 23 hours hold. Part 4. Hours 2 to 6. The other side of the planet. Ask a different question now. Not what is happening at Chicxulub. Not what is happening along the Gulf Coast of North America. Ask what is happening on the other side of the planet, in the places where the ground has not shaken yet, where the sky is still dark, where the animals are going about the ordinary business of being alive in a world that is, from their immediate perspective, completely unchanged. Because the story of the first 24 hours is not only the story of the impact zone, it is the story of how a single event in one location dismantles the conditions for life across an entire planet. Not through direct destruction, but through a sequence of physical mechanisms that operate at different speeds and reach different places at different times. Understanding that sequence is understanding how a mass extinction actually works. It is not a single blow. It is a cascade. The seismic wave reaches the opposite side of the planet within 20 minutes of impact. It does not arrive as a single sharp jolt the way a local earthquake arrives. By the time it has traveled through 20,000 kilometers of rock and mantle, it has spread, refracted, reflected off internal boundaries within the Earth, and arrived as a complex of waves coming from multiple directions simultaneously. The effect at the surface is unusual and deeply unsettling to any animal sensitive to ground vibration, which is to say, almost every animal on Earth. The ground moves in ways that do not correspond to any normal seismic pattern. It does not shake in one direction and stop. It oscillates. It ripples. In some locations, the seismic energy focuses due to the geometry of the crust and produces surface shaking more intense than any earthquake those fault systems would naturally generate. Volcanic systems that were already under pressure respond. The relationship between large impacts and volcanic activity is not simple, and the scientific community continues to refine its understanding of it. What is well established is that the seismic energy from an impact of this magnitude is sufficient to destabilize magma chambers that are already close to their threshold for eruption, triggering events that would not have occurred on that timeline without the impact In India, the Deccan traps volcanic province, already one of the most active volcanic systems on the planet at this time, is producing enormous quantities of lava and volcanic gas. The precise relationship between the Chicxulub impact and the Deccan traps eruptions is still debated by geologists. What is not debated is that the impact did not occur in a geologically quiet world. It struck a planet that was already under stress. 2 hours after impact, the sky over Asia begins to change. Not with fire, not with heat, with light. The spherules that were thrown into space in the first seconds after impact have been traveling on ballistic trajectories, arcing through the vacuum above the atmosphere, and they are now beginning to re-enter over the eastern hemisphere. From the ground, the effect is visible first as an intensification of the stars, a brightening of the sky that seems at first like a peculiar aurora. Then, as individual streaks of light multiplying across the entire visible sky until the streaks are too numerous to count and the sky is not dark anymore. It is not dawn. It is something that has never happened before in the experience of any animal that has ever lived on this planet. Every point of the sky is a source of light and heat simultaneously. And the heat is increasing. An animal standing in open terrain in what will become eastern China, 2 hours after the impact, is not being struck by falling debris. The spherules are too small and too numerous for individual impacts to be the primary danger. The danger is thermal. The sky above is radiating heat downward onto every exposed surface, and the intensity of that radiation is increasing as more spherules arrive and as the ones already in the upper atmosphere continue to transfer their kinetic energy into heat. The temperature at ground level in open terrain rises, not by 1 or 2 degrees over an hour in the way that a warm afternoon develops, by tens of degrees in minutes. The rate of temperature increase in the most exposed locations during peak spherule re-entry is comparable to the rate of temperature increase inside a conventional oven set to its maximum temperature. Rock surfaces reach temperatures sufficient to ignite dry organic material on contact. Forests that have stood for millions of years begin to burn not from below, where fire normally starts, but from above. As the canopy catches first and the heat works its way down, the fires in Asia and in Europe and across the southern hemisphere are not caused by the impact directly. No fragment of the asteroid reaches these places. No shock wave destroys these forests. They burn because of physics, because the kinetic energy of 100 trillion glass beads re-entering the atmosphere is sufficient to raise the temperature of the lower atmosphere across the entire planet by enough to ignite exposed, dry vegetation. Not everywhere, not uniformly. The distribution of heat depends on local conditions, on cloud cover, on the moisture content of the vegetation, on terrain that provides or denies natural shielding. A forest that happens to be experiencing its wet season burns less readily than one in its dry season. A landscape with significant cloud cover receives less thermal radiation from the spheral re-entry than a clear sky location. The extinction is brutal, but it is not perfectly uniform. These variations in local conditions, this patchwork of more and less severe thermal exposure, will matter enormously for what survives. 3 hours after impact, the sulfur enters the story. The rock beneath the Yucatan Peninsula is not ordinary crust. It is extraordinarily rich in sulfur-bearing minerals, primarily anhydrite, formed from hundreds of millions of years of evaporated shallow seas, depositing their dissolved minerals as solid layers in the seafloor sediment. When the asteroid vaporized this rock, it did not simply produce a cloud of generic rock vapor. It produced a cloud that was extraordinarily rich in sulfur dioxide and sulfur trioxide, gases that behave very differently in the atmosphere from the carbon dioxide and water vapor that dominate most volcanic emissions. These sulfur gases are now rising. They are moving upward through the atmosphere with the thermal plume of superheated material that the impact sent skyward. They will reach the stratosphere within the next several hours. And once there, they will do something that will define the next several years of life on this planet, far more than the fires or the tsunami or the direct thermal pulse. They will convert to sulfuric acid aerosols, microscopic droplets of acid suspended in the upper atmosphere, reflecting incoming solar radiation back into space before it can reach the surface. But that is not a story for today. Today, 3 hours after impact, the sulfur is still rising. Its effects are still hours and days and weeks away. Today, the planet is still hot, 4 hours after impact. The pattern of fire across the northern hemisphere is visible in the geological record in a way that almost nothing else about this event is. A layer of soot and charcoal, found in rocks of this age at dozens of locations across North America, Europe, and Asia, tells a story of simultaneous, widespread combustion of organic material on a scale that has no parallel in the entire geological record of the last 500 million years. The layer is thin. In some locations, it is less than a centimeter thick, but it is everywhere. And its chemical composition tells geologists exactly what burned and approximately when. What burned was the world, not every tree, not every plant, not the waterlogged vegetation of swamps and riverbanks, not the root systems of grasses and ferns that will prove critical to the recovery that will eventually come, but the exposed surfaces of the terrestrial world, the canopies of forests, the dry grasslands, the exposed organic material on the surface of the soil. These burned across an area that represents a significant fraction of the land surface of the northern hemisphere within the first 6 hours after impact. 5 hours after impact, the ocean is a different kind of story. The deep ocean is not burning. The deep ocean does not know that anything has happened. At a depth of 2,000 meters, the water is cold and dark and completely insulated from the thermal events occurring at the surface. The pressure at that depth means that the organisms living there are not affected by changes in surface temperature, by fires, by the spherule re-entry, by any of the direct physical consequences of the impact. They are, at this moment, in the safest environment on the planet. This will not remain true indefinitely. The collapse of the food chains that supply organic material to the deep ocean will eventually affect even the deepest marine communities. But that collapse takes months to propagate downward through the water column. For now, 5 hours after impact, the organisms of the deep ocean are the only significant population of complex life on Earth that is experiencing a completely normal day. The contrast is almost incomprehensible. On the surface of the land, across 2 hemispheres, the world is burning or has burned. The sky is still bright with the diminishing light of spherules re-entry. The temperature in open terrain is beginning to fall as the peak of the thermal pulse passes, but the fires it ignited are sustaining themselves now on their own fuel, consuming the organic material of forests that took millions of years to develop. In the deep ocean, 2,000 meters below all of this, a fish that has been swimming in cold, dark water for its entire life continues to swim in cold, dark water. It has felt the seismic wave. It registered as a disturbance in the water pressure, a brief anomaly, and then it was gone. Everything since then has been normal. 6 hours after impact, the direct thermal killing phase is substantially over. This does not mean the dying is over. It means the fastest mechanism of death. The thermal pulse from spherules re-entry has delivered most of its energy to the surface. the fires will burn for weeks. The sulfur aerosols will continue rising into the stratosphere for days. The collapse of food webs will take months to propagate through ecosystems. The cooling that follows, when the aerosols block enough sunlight to drop global temperatures significantly, will last for years. But the most intense phase of the most violent day in the history of complex life on this planet is ending. What remains is something quieter and in many ways more absolute. Bartsank. Hours 6 to 24, when darkness follows fire. There is a specific quality to the silence that follows catastrophic fire. Anyone who has walked through a forest after a wildfire knows it. The absence of bird calls. The absence of insect sound. The absence of wind moving through leaves because the leaves are gone. The occasional crack of a cooling branch. The smell of ash and wet char if it has rained. Or the smell of dry ash and exposed mineral soil if it has not. It is not peaceful. It is the specific silence of a place where the systems that produce sound have been removed. Multiply that silence across a continent. 6 hours after impact. Across the majority of the land surface of the Northern Hemisphere, the fires that the spherule re-entry ignited are still burning where they have fuel, where they have consumed everything available. They have stopped, not because they were extinguished, but because there is nothing left to sustain them. The landscape in these areas is not dramatic in the way that the impact itself was dramatic. It is flat and grey and still. The canopy is gone. The surface of the soil is exposed. The mineral earth beneath the organic layer is visible in a way that it has not been visible in these locations for millions of years. Since before the forests that just burned were established, the sky above this landscape is changing. During the peak of the spherule re-entry, the sky was bright with the light of friction-heated glass beads. That light is now fading as the last of the spherules complete their re-entry and the atmosphere begins to process the energy they deposited. What replaces the brightness is not the ordinary blue of a clear sky. It is something intermediate, something hazy. The upper atmosphere is beginning to fill with 2 distinct categories of material that will define the character of the sky for a very long time. The first is soot. The fires burning across the Northern Hemisphere are injecting enormous quantities of fine carbon particles into the atmosphere. Individual particles of combustion soot are small enough to remain suspended in the upper atmosphere for months without settling. They are also efficient absorbers of solar radiation, meaning that a sufficiently dense layer of soot in the upper atmosphere does not simply block sunlight, it absorbs it, warming the upper atmosphere, while simultaneously preventing that energy from reaching the surface below. The second is the sulfur. The sulfuric acid aerosols forming from the sulfur gases injected into the stratosphere by the impact are not yet a complete layer. They are still forming, still rising, still being distributed by stratospheric winds, but the process is underway, and the aerosols forming in the stratosphere above the impact site are already beginning to affect the quality of light reaching the surface below. By 8 hours after impact, in the regions where the fires have burned through their available fuel and stopped, the light is wrong, not dark, not night, wrong. The sun is still above the horizon in some locations, and below it in others as the planet rotates through its normal cycle. But the quality of the sunlight reaching the surface through the thickening haze of soot and early aerosols is diminished in ways that are measurable and that matter biologically. Photosynthesis, the process by which plants convert sunlight into energy, begins to slow when light intensity drops below certain thresholds. Those thresholds are not being crossed everywhere yet, but in the most heavily affected regions, in the areas directly downwind of the largest fire systems, the light is already inadequate for normal photosynthetic activity. The plants that survived the thermal pulse are beginning to experience something new. Not heat, not fire, insufficient light. This transition from the acute violence of the impact day to the chronic deprivation of the impact aftermath is the hinge point of the entire extinction event. Most of the animals that died in the first 6 hours died from direct physical causes, from thermal radiation, from fire, from the tsunami, from the seismic events. Most of the animals that will die in the weeks and months that follow will die from something much slower and much harder to escape. They will die because the food is gone. But that is not yet the story of today. 10 hours after impact, something unexpected is happening in certain locations across the southern hemisphere. It is raining. The impact injected an enormous quantity of water vapor into the atmosphere, along with the rock vapor and the sulfur gases. Water vapor condenses around particulate matter, and there is now an extraordinary abundance of particulate matter in the atmosphere. In some regions of the southern hemisphere, distant from the fires and from the direct debris cloud, but within the range of atmospheric circulation patterns that are carrying fine particles from the impact, rainfall is occurring. Acid rainfall, incorporating sulfur compounds from the impact plume. Rainfall that is not clean in any sense that organisms have previously experienced, but rainfall nonetheless. The effect of this rainfall on the landscape is not straightforward. It suppresses some fires. It deposits acid onto vegetation that survived the thermal pulse, causing chemical stress on leaf surfaces and soil chemistry. It washes fine particles from the atmosphere, temporarily improving visibility in some locations, before the ongoing injection of material from fires and the continuing volcanic activity restores the haze. It creates a landscape that is damaged in multiple, simultaneous ways, none of them individually lethal to every organism, all of them accumulating into conditions that most complex ecosystems cannot sustain. 12 hours after impact, the planet is in a state that has no precedent in the experience of any living organism. The northern hemisphere is largely dark, with smoke and ash. The fires are still burning in areas with remaining fuel. The sky is a color that has no name, because no living thing has ever needed a name for it before. Brownish, yellowish, lit from above by a sun that is present but muted, its light scattered and absorbed by the thickening atmospheric load of particles and aerosols. The temperature in areas that have burned is beginning to drop, not because night has fallen, but because the insulating canopy is gone and the heat that the soil absorbed during the thermal pulse is radiating back into the sky without the vegetation that would normally slow that process. In the deep river valleys, in the cave systems of limestone karst terrain, in the burrows beneath the root systems of trees that survived, small things are still alive. They are not comfortable. The air is acrid with smoke. The smell of burning is everywhere. The sounds of the world they knew, the calls of other animals, the rustling of vegetation, the ambient noise of a functioning ecosystem are absent, but they are alive. Their metabolisms are slow enough that they can survive for extended periods without food. Their bodies are small enough that the temperature fluctuations of the damaged surface environment are not immediately lethal. They are in the right kind of wrong place. 16 hours after impact, on the other side of the planet from Chicxulub, the Indian Ocean is experiencing something that the instruments of modern oceanography would record with considerable alarm, if any existed to record it. The seismic wave that passed through the Earth's interior in the first 20 minutes after impact triggered submarine landslides along multiple continental shelf margins in the Indian Ocean basin. These landslides, the collapse of sediment that had been accumulating on the edges of continental shelves for millions of years, have generated their own secondary tsunami waves. much smaller than the Chicxulub wave, but significant by any other standard. These secondary waves are now reaching coastlines across the Indian Ocean region, arriving without warning. Their origins so distant and indirect that no surface evidence of the impact has yet reached the organisms living on these coastlines. Animals on the beaches of what will become Madagascar are experiencing a tsunami generated by an earthquake they did not feel, caused by an impact they cannot know about. On the other side of the planet, the chain of causation is so long and so indirect that it would be invisible even to a human observer with full knowledge of the situation. To the animals experiencing it, it is simply the ocean doing something the ocean has never done before, for no reason that any available sense can detect. 20 hours after impact, the fires across the northern hemisphere are beginning to run out of fuel in the most heavily burned areas. Not because they have been extinguished, because they have finished. The organic material that was available to burn has been consumed, and what remains is mineral soil and the carbonized remnants of root systems and the ash of what were, yesterday, forests that had been accumulating biomass for millions of years. The silence in these areas is now complete in a way that it was not complete at 6 hours after impact, when the fires were still active and producing sound and heat and light. Now there is nothing. The wind moves across bare mineral soil. The sky above is a uniform pale brown. There are no animals calling. There are no insects. There are no birds. There is no sound of water moving, because the watercourses that ran through these forests have been altered by the loss of the vegetation that regulated their flow, and some of them have simply stopped running. Their sources of groundwater recharge, disrupted by the destruction of the root systems that maintained soil permeability. This is what the end of a world actually looks like. Not the impact, not the fireball, not the wall of water. Those things are violent and dramatic, and they kill enormous numbers of organisms very quickly. But the end of the world looks like this. It looks like bare mineral soil where forest was. It looks like a sky, the color of old bruises. It looks like the complete absence of the sounds that define a living ecosystem. It looks like nothing moving that is large enough to see. 24 hours after impact, the planet is alive. That sentence requires emphasis because it is surprising and because it matters. The planet is alive. The extinction that the Chicxulub impact will ultimately produce, an extinction that will eliminate roughly 3/4 of all species on Earth, has barely begun. Most of the species that will eventually disappear are still present at this moment, either as surviving adults in protected locations, or as eggs, or as seeds, or as spores, or as juvenile organisms that have not yet been exposed to the conditions that will eventually kill them. The process that will remove them from the planet will take thousands of years in some cases. It is not a single day's work. What the first 24 hours have done is something more specific and more important than killing. They have broken the systems. The food webs that sustained the large herbivores are compromised. The plant communities that will eventually recover are present in fragments and in seed banks and in the surviving root systems of burned forests. But they are not producing the biomass that multi-ton dinosaurs require. The atmospheric conditions that allowed complex photosynthesis to occur across the full range of the planet's land surface are disrupted in ways that will take years to resolve. The ocean chemistry is beginning to change as acid rainfall alters the pH of surface waters in ways that affect the carbonate chemistry on which marine shell-forming organisms depend. None of these systems will recover to their previous state. That is the true meaning of the first 24 hours. Not the number of organisms that died, not the scale of the fires, not the size of the tsunami. The true meaning is that the conditions which made the Cretaceous world possible, which sustained its complexity, for 165 million years, which allowed Tyrannosaurus and Quetzalcoatlus and the mosasaur in the shallow sea of the Yucatan to exist as the culmination of an extraordinarily long and successful evolutionary experiment. Those conditions ended in a single day. The experiment did not end that day. The ending took time, but the conditions for the experiment ended at approximately 6 in the morning, 66 million years ago, when the sky above a shallow warm sea turned white and stayed white. By the end of the first day, the impact itself was over. What had just begun was everything else. Part 6. Who survives and why? Lessons from the first day. Survival on this day is not a story about strength. It is not a story about intelligence. It is not a story of speed or size or the complexity of an organism's nervous system or the sophistication of its social behavior. The filter that the first 24 hours applies to life on Earth is not a test of biological quality in any meaningful sense. It is a test of geometry and metabolism and the specific accident of where an organism happens to be when the sky changes. Understanding who survives and why requires setting aside almost everything we instinctively believe about what makes an animal successful. The most successful animals on Earth at the moment of impact, the ones that have dominated terrestrial ecosystems for 165 million years, are about to demonstrate that success in a previous environment is not a guarantee of survival in a new one. And the least successful animals on Earth at the moment of impact, the ones occupying the margins and the burrows and the spaces between the things that matter, are about to demonstrate something else entirely. Start with the ones that do not survive. The large non-avian dinosaurs are not killed by the impact directly. Very few of them are close enough to Chicxulub to be killed by the immediate physical effects of the strike. What kills them is a combination of factors that operate on the timescale of days and weeks and months. And the first 24 hours establishes each of those factors clearly. The first factor is body size. A Tyrannosaurus rex requires an enormous quantity of food to sustain its metabolism. Estimates of daily caloric requirements for large tyrannosaurs range from 40 to 140 kilograms of meat per day, depending on whether they were fully warm-blooded in the modern mammalian sense or something intermediate. Either way, the food web that supplies this quantity of meat is a complex structure. It requires large populations of large herbivores. Large herbivores require functioning plant communities producing sufficient biomass. Plant communities require adequate sunlight and adequate soil chemistry and adequate moisture. Every link in this chain is compromised within the first 24 hours. A Tyrannosaurus that survives the impact day physically intact is already living in a world that cannot sustain it for much longer. It does not know this. It is simply hungry, and the things it would normally eat are becoming harder to find. The second factor is thermal regulation and energy budget. Large animals lose heat more slowly than small animals relative to their body mass, which is generally an advantage in cold environments. But in the immediate aftermath of the impact, during the thermal pulse phase, size is a liability. A large animal has more surface area, absorbing thermal radiation, and less ability to access the underground environments that provide shielding. A small animal can fit in a burrow. A Tyrannosaurus cannot. The third factor is generalism versus specialism. The large dinosaurs of the late Cretaceous are, in many cases, highly specialized for specific ecological roles in a specific kind of world. Hadrosaurs are specialized for processing large quantities of plant material of the kinds that late Cretaceous forests produce. Tyrannosaurs are specialized for hunting large prey animals of the kinds that late Cretaceous ecosystems support. When the ecosystems change, the specializations that made these animals successful become the constraints that prevent them from adapting. Now, consider the ones that survive. The birds are the most important survivors to understand, because they are the most counterintuitive. Birds are dinosaurs. This is not a metaphor or an analogy. Birds are the living members of the theropod dinosaur lineage, the same lineage that produced Tyrannosaurus and Velociraptor, and the feathered dinosaurs of the Cretaceous forests. At the moment of impact, there are dozens of lineages of birds alive, many of them quite different from the birds we know today. Most of these lineages will not survive the extinction. The birds that survive and eventually diversify into the more than 10,000 species alive today are a subset of the avian diversity present at the time of the impact. What do the surviving bird lineages have that the non-surviving ones lack? The answer that emerges from the fossil and genetic record is not a single trait. It is a combination. The bird lineages that survive tend to be smaller. They tend to be more generalist in their diet, capable of eating seeds and invertebrates and plant material, rather than being restricted to a narrow range of food types. Seeds are critical here. Seeds are the stored energy reserves of plants, designed by evolution to survive unfavorable conditions and remain viable for extended periods. In a world where the living plant biomass has been devastated by fire and darkness, seeds represent a food source that persists in the soil long after the plants that produce them are gone. A bird that can eat seeds can survive in a burned landscape in a way that a bird specialized for catching large insects in forest canopy cannot. The crocodilians survive, and their survival is instructive in a different way. Crocodilians at the time of the impact are not dramatically different from modern crocodilians. They are semi-aquatic ambush predators, spending much of their time in water, capable of going for extended periods without food, eating a wide range of prey, including fish, invertebrates, carrion, and whatever terrestrial animals come within reach of the water's edge. They are, by metabolism, extremely efficient. A large crocodilian can survive for months without eating by reducing its metabolic rate to the minimum necessary to maintain basic biological function. This metabolic flexibility is the key to their survival. In the weeks and months after the impact, when food becomes scarce and the energy cost of finding it increases, the ability to wait, to slow down, to exist on almost nothing for extended periods, is the single most valuable biological trait an animal can possess. Crocodilians have been refining this trait for hundreds of millions of years. They are, in a sense, perfectly pre-adapted for the world that the impact creates. The turtles survive for similar reasons. Semi-aquatic, capable of extended periods of metabolic dormancy, omnivorous enough to process whatever organic material is available, protected from the thermal pulse by the water they inhabit and by their shells, small enough to access sheltered environments. They are not the most complex animals in the Cretaceous world. They are among the most durable. The small mammals survive, and their survival is the most consequential of all for the story of the next 66 million years. At the moment of impact, the mammals are not a single, unified group with a single survival strategy. They are a diverse collection of small, warm-blooded animals occupying a wide range of ecological niches. Almost all of them small. Almost all of them primarily nocturnal or crepuscular. Almost all of them capable of surviving on a diet that includes insects and seeds and whatever other organic material they can find. They live in burrows and rock crevices and beneath the leaf litter of forest floors. They are warm-blooded, which means they can remain active in temperature conditions that would render cold-blooded animals sluggish and vulnerable. They have high reproductive rates relative to the large dinosaurs, meaning that populations that are decimated can recover more quickly if conditions improve. the specific lineage of mammals that will eventually produce the primates, and through the primates, the hominids. And through the hominids, the species reading these words is present on this day. It is not an impressive organism by any standard that the Cretaceous world would recognize as impressive. It weighs somewhere between 10 grams and 1 kilogram, depending on which specific ancestral species we are identifying. It is nocturnal. It lives in burrows or in the dense root systems of forest floor environments. It eats insects primarily, supplemented by whatever seeds and plant material it can find. It has a brain that is large relative to its body size. But this brain is not providing it with any conscious understanding of what is happening today. It is simply responding to immediate conditions with the behavioral repertoire that its evolution has given it. On the morning of the impact, it was in a burrow. It survived the thermal pulse because the soil above it provided insulation. It survived the fires because the fires did not reach the depth of its burrow. It will survive the next weeks and months because it can subsist on insects and seeds in quantities that the devastated landscape can still provide. It will reproduce because that is what it does, and its offspring will inherit the world that is forming in the ash and the silence of the Cretaceous aftermath. It does not know any of this. It does not know that the animals that dominated the world above its burrow for 165 million years are gone or going. It does not know that the world it will emerge into, when conditions eventually improve enough to make emergence worthwhile, will be a world with vacancies in every ecological role that the large dinosaurs previously occupied. It does not know that those vacancies represent an opportunity that its lineage will spend the next 66 million years filling, producing in the process the elephants and the whales and the great apes, and eventually the particular branch of the great apes that will stand upright and look at the sky and wonder what it was like on the day the asteroid came. It knows that it is alive, in the burned and silent world above its burrow. On the first night after the last ordinary morning, that is enough. 24 hours after impact, the crater at Chicxulub is cooling. Not quickly. The rock that was melted and re-solidified in the first minutes of the impact retains heat the way that thick stone retains heat. Slowly, releasing it in increments over days and weeks. The center of the crater, where the deepest and most intensely heated material was deposited, will remain warm to the touch for years. The geological structure that will eventually be identified by geophysicists in 1991, buried beneath a kilometer of younger sediment and the shallow waters of the Gulf of Mexico, is at this moment still settling into its final form. The last adjustments of the collapsed crater walls, the final positioning of the central uplift structure, the slow infilling of the impact melt sheet as it cools from the outside inward. The crater is 180 kilometers across. It is the largest structure on the surface of the Earth that was created in a single day. Above it, the atmosphere is a record of everything that happened in the last 24 hours. The soot from the fires of North America and Asia and Europe is distributed through the upper troposphere in concentrations that will take months to settle. The sulfuric acid aerosols forming in the stratosphere are not yet complete in their global distribution, but the stratospheric winds that circle the planet are carrying them eastward and westward from the impact site. And within the next several weeks, they will form a layer that covers the entire planet. This layer will persist for years. During those years, it will reflect enough incoming solar radiation to drop the global average surface temperature by somewhere between 10 and 15 degrees Celsius. For a planet that was already 10 degrees warmer than today, this is not simply a correction. It is an overcorrection of catastrophic proportions. The organisms that survive the heat of the impact day will face, within months, a cold that their evolutionary history has not prepared them for. But that is not the story of today. Today, 24 hours after impact, the fires are still burning in the areas that have fuel remaining. The acid rain is falling in parts of the southern hemisphere. The seismic adjustments triggered by the impact are still working their way through fault systems across the planet. The mosasaurs in the surviving sections of the western interior seaway are alive but disoriented. The chemistry of the water around them beginning to change in ways that will become lethal over the next weeks, as acid precipitation alters the carbonate balance of the shallow inland sea. The hadrosaur herds that survived the thermal pulse in sheltered river valleys are alive and hungry in a landscape that looks nothing like the landscape they fed on yesterday. The sky everywhere on Earth is wrong, not dramatically wrong in every location. In parts of the southern hemisphere, in areas that experienced neither the direct thermal pulse nor the worst of the fire-generated soot, the sky is simply hazy. The sun is visible, but diminished. The quality of the light is off in a way that would be difficult to quantify but impossible to ignore. In the most heavily affected areas of the northern hemisphere, the sky is the color of ash, and it will remain approximately that color for weeks. 66 million years from this moment. A species will exist that is capable of looking back at this day and reconstructing it. That species will find the evidence in a layer of rock approximately 1 centimeter thick, distributed across the surface of the planet at the geological boundary between the Cretaceous and the Paleogene periods. The layer contains iridium, an element rare in the Earth's crust but abundant in asteroids. Deposited globally by the spherules and the vaporized material of the impact, it contains shocked quartz, mineral grains deformed by the pressures of the impact in ways that no geological process other than impact or nuclear explosion can produce. It contains spherules of resolidified impact glass. It contains a spike of soot consistent with global wildfires. It contains, in many locations, an abrupt transition from a fossil assemblage rich in large, complex organisms below the layer to a fossil assemblage dominated by small, generalist organisms above it. This layer is called the KPG boundary. It is one of the most studied geological features on Earth. In some locations, it is visible to the naked eye as a thin, dark line running through an exposed cliff face or a road cut. You can put your finger on it. You can touch the exact moment when the Cretaceous ended and the Paleogene began. The moment when one world stopped and another, slower world started building itself from what remained on this side of that line. 24 hours after impact. The building has not yet begun. What exists is the raw material, the surviving organisms in their burrows and their river channels and their ocean depths, the seeds in the soil of the burned forests, the root systems of ferns, which will be among the first plants to recolonize the devastated surface. Their spores already present in the soil, waiting for conditions that will allow germination. The bacterial communities in the soil that decompose organic matter and recycle nutrients, largely unaffected by the events of the last 24 hours. Continuing the chemical work that makes soil fertile and eventually makes plant growth possible. The planet is not dead. It is emptied of most of what made it the specific world it was. The large animals that defined its ecosystems are gone or going. The plant communities that sustained those animals are devastated across much of the northern hemisphere. The atmospheric conditions that allowed complex photosynthesis to proceed normally across the full range of the planet's land surface are disrupted in ways that will take years to resolve. But the raw material is present. The planet will take millions of years to rebuild the ecological complexity that was lost in a single day. It will not rebuild it the same way. The world that emerges from the Cretaceous extinction will be organized around different animals, occupying different roles, using different biological strategies than the world that existed before the impact. It will be, in its own terms, just as complex and just as rich and just as capable of producing organisms of extraordinary sophistication. It will simply be a different world, built from the survivors of a morning that none of them understood, and none of them chose, and none of them could have prepared for. The crater at Chicxulub continues to cool. The fires continue to burn. The small mammal in its burrow breathes in the dark. In the weeks that follow this day, the sky will darken further as the sulfur aerosols complete their global distribution. Temperatures will begin to fall. The ferns will be among the first plants to return to the surface of the burned land, their spores more resistant to the disrupted conditions than the seeds of the flowering plants and conifers that dominated the Cretaceous forests. The collapse of marine food webs will accelerate as the darkness reduces phytoplankton productivity in the surface ocean, removing the base of the food chain that supports everything above it. The large dinosaurs, the ones that survive the impact day in sheltered locations, will find food increasingly difficult to locate and will begin dying not from violence but from starvation, one by one, in a process that will take thousands of years to complete in some lineages, but that is already, on this first morning after, inevitable. That is a different story. This one ends here, 24 hours after the last ordinary morning that the Cretaceous world will ever have, with a crater cooling in the dark, with fires burning in the distance, with the wrong sky above a planet that is, against considerable odds, still alive. The first day is over. What it started will take millions of years to finish.